Again, welcome everyone to our webinar today on data calculations in ARM. So we'll utilize maybe the assessment ratings that have been taken already in ARM to create new assessment columns, some new calculations and different things we can do with that data. So a variety of different topics here to cover. So let's dive in. The first topic to cover are control corrections. And this is a somewhat common thing to do in a variety of different types of research. The idea being that we want to calculate efficacy relative to the untreated plots in our trial. And efficacy is really a percent reduction. So we're kind of forcing the check to be zero, that nothing has happened. So there's the check is no response in that sense. And then all of the other treatments, the assessment values, we are converting relative to what happened in those check plots. So kind of the most common one, at least that we hear and get questions on, would be the Abbott's calculation. And that is designed originally for infestation ratings on a uniform population. And there's actually kind of a variety of slightly different ways to calculate this efficacy value, and trying to kind of summarize and put those all together here. They end up in a variety of spots in ARM. So trying to make sense of the different options. They're really all just different ways to calculate this efficacy, and what do we want to use for the check? How do we calculate this relative information? So the first one in our table, the tab. So on the left here, I have that transform. So that would be what you enter in ARM in the ARM action codes field for a column. It'd be you would go into a new empty column and choose that code, and it'll create a calculated column for us based on the source column that you want to transform. And that would be that N. So instead of putting literally the number N, you would choose a column number. So this tab would be we'll just call it classic Abbott's for lack of a better term, kind of the baseline here. And that calculation, we are referencing the check in the same replicate as the assessment value that we're transforming. So as a result, we get unique values for each plot. And it's really designed, oops, scroll bar always gets me, really designed for when the performance in the check is pretty consistent. So across the different replicates, if we more or less have pretty much the same response in the check plots, then this tab is great to use. Then each and every assessment value that we recorded is compared to the check in its own replicate to create this efficacy, this percent reduction calculation. Now, if we don't quite have that assumption that the check's really the same, maybe there was some variation within just the check across different replicates. So if we didn't quite have even pressure from our pest, then there might be some concern about just using the same replicate, because of course, how much of that response that we calculated, how much of that is due to the actual treatment versus the amount of pressure in that one replicate in the check plot. So instead of confounding all of that and making us a little less certain about things, let's instead generalize the check. So utilizing the @U tab, that will use the mean of all of the checks across those replicates. So we'll really say, well, those checks are kind of varied so much. Let's just take an average of all the check plots in this trial and use that value as our relative, our measuring stick for each and every assessment value that we're trying to calculate. So we'll still get per plot, we'll get a unique value for each plot that we calculate, but we've just kind of covered ourselves in case there's an uneven amount of pest pressure coming in. Now, if we really see even worse, where there's really not a ton of consistency across the whole trial, maybe our replicates, our blocking was successful in that we blocked things so our replicates are fairly homogeneous, but each individual replicate compared to each other, lots of variation, didn't have much consistency there, then we're really better off just using the mean of the treatment versus the mean of the check. So that would be the T-tab transformation. And the big difference, there is kind of a fundamental shift using that transformation, because now we're really only getting one unique value per treatment because we're using the mean of the treatment. Kind of a last, obviously given the choice, we get a lot more information by calculating per plot, but depending on what happened at the individual trial, this might be kind of your only option. It does make for a nice summary. You get one value calculated for each treatment, and it's relative to the check. And there is an option to have this value calculated, not really in its own assessment column, but just in your report output. So there is an automatic percent control is what this APC code is short for. You could put that in the original column to be able to see this T-tab value, but just on the report. So it doesn't save it in the trial. If you've got a database where you're going to export the data out to, that isn't going to end up there. It's kind of only this temporarily calculated when you're generating a report. But it does look pretty nice if that is what you'd want to see there. So let's toggle over to ARM. I don't have an example for all three of those combinations, but hopefully just to demonstrate how any one of these would work, I have a trial here open that has a variety of assessment columns. So we'll come back and forth throughout this session for the different types of calculations. And what I've done, if you haven't seen this before, in the assessment view options, I have defined a sort. I'm actually sorting on this field that I just used to make a little code to remind myself what example we're on, but I have sorted my columns by that field, and then using this display sort as tabs, I get almost like an Excel sheet, if you will, type of view that shows me all the different, in this case, all the different values I've typed in my sort order for view. So that's just the little engine here of how I'm toggling to see only the columns that we want to talk about at this one time. So our first example for our control correction, I've got a pest severity rating on leaves, different subsamples that I've recorded. And what I wanted to do then is calculate that Abbott, that efficacy. So I created a new assessment column right next to it in this case. And the action code I used was the TAB. If I bring up the action codes field, you'll see that there's quite a variety of different calculations, and we'll cover a good portion of those today. And I chose the Abbott percent of untreated transformation. And when I clicked on this, it doesn't know the column number yet. So ARM pops up and asks me, what column number are you wanting to calculate from? Or if you kind of start to memorize these action codes, it's also entirely possible just to type in tab and then the brackets and then 1. And then it'll just automatically fill in for you. But usually picking from the list is easiest, so you don't type the wrong thing in and get the wrong calculation or anything like that. So you can see here in this calculation for all of the treatment 1, that's my check treatment, the calculation results in a 0 for all of them. And then the rest of these are calculating that reduction amount relative to the check. And it's somewhat deceiving here. I'm like, why do I have 74% for a 0, but there are the subsamples here? So there is some presence of that pest here, which is why we had the 74. And then real quick to show this APC. So I put this in the first column. So this is the calculations equivalent to the T tab, what number we actually get in the end, but it's one of these automatic transformations, which means that it only will happen once we get to a report. So I'll just real quick generate an AOV report, and I want to make sure that I show only the current view. Actually, it's the first 2 columns anyway, so I can just preview on the screen. Well, I've got a lot of things turned on. Let me turn off some of those descriptions so it's just easier to see what we're looking at. And I'll zoom in because obviously this is very small. But here for that column 1, that APC is giving us these percentages as well. So without the APC, you get your treatment mean and the mean comparison test, but then there's this additional Abbott's value, which does kind of look nice. It gives you a good reference point. It's not used statistically. There's no separation on those percentage values, but it just gives a nice readout kind of for your reference to see relative to the check treatment, what were these at? So for example, treatment 3, we got about 2/3 controlled. We obviously weren't down to 0 where we eliminated all of the pests entirely, which would have resulted in a 100% control. We controlled 100% of the pest. We controlled about 2/3 of it in this case. And then there is a question, good catch here, looking at those percent values on the APC, they don't quite match the tab over here. And that is because they are a slightly different calculation. If I go back to my slideshow here, we had column 2 was the tab. So that was calculating each individual value relative to the check in its own replicate. And so then we get numbers per plot. And then on the report, we were seeing the average of those individual calculated values. The APC, which is equivalent to the T-tab numbers, that was using the overall treatment average. So the overall average treatment 2 versus the average check value. So it is numerically just slightly different. And if we wanted to, we could calculate and kind of compare maybe column 3, we insert a new column and do T-tab to see 1 by 1. As you can tell, it doesn't make huge difference numerically. Obviously, it probably depends on exactly what numbers are there. You probably get roughly the same result in the end. But I think it's an important distinction to make. And a lot of times, at least just the casual questions and comments we hear, not being researchers, just the term I want to run an Abbott's is thrown around a lot. So I think it's just important to kind of make these distinctions that although numerically you might arrive in a similar spot, there are some technical differences, and kind of considering what you want to do, it definitely makes a difference. A couple more efficacy calculations that are possible. So Abbott's, like I said, kind of the most popular one, most common, and I think most generalized as well. I'm sure there's certain industries that rely more than others, but there isn't anything inherently specific to that one industry that it originates in. But there are a couple more calculations that are utilized as well. There's a Henderson-Tilton, and the code for that in ARM THT that can be used on a infestation, again, where we're looking at our pest, but for a non-uniform population. And the big idea with this is that you have to go out before your application to perform a pre-treatment assessment. So, if we really can't assume that our pest population is going to be uniform, we should go out ahead of time before anything really happens in the trial, or at least before that application happens, go out and take an assessment beforehand. Then we make that application, and then we come out later and take another assessment after the treatment happened. And so we know a little bit more about each individual plot, and then this Henderson-Tilton calculation can utilize that pre-treatment assessment to give us a calculation in the end. So that's the Henderson-Tilton, and you would just specify both the pre-treatment assessment column and then the post-application column. And then there's also the Schneider-Orelli, and that is TSO is the code. That's a mortality rating. Again, kind of assumes a uniform population. So those are just other examples, other codes that you'll find in ARM. ARM can calculate these as well. All right, one more set of control corrections, and this would be when you want to calculate a percent of check. Slightly different, sounds very similar to the Abbott's. Again, we're wanting to gauge the performance of a treatment relative to a control, but more commonly, or for this one, it's when you're looking at a positive effect. So something like yield or emergence, where you would really want to set that check at 100, and then anything, did the treatment make things better? It would be over 100, 110% of check. How much better did the plots perform with whatever treatment that we're looking at? So two of them here, so similar to the Abbott's as far as our options and how things can be calculated. We have the first one is UPOC, UPOC. And that transformation, we are using the check in the same replicate. So a per plot calculation, if we can assume that the check are at least reasonably consistent, then we want to calculate using the check in our own replicate. So that's much like our discussion with the tab, with kind of that regular Abbott's, if you will, but when you're doing the percent of check, that would be UPOC. So the check will be 100. And then everything else will kind of fit in from there. Hopefully all of your products are above 100, but it's technically mathematically feasible. It could be under 100 if it slipped and did not do as well as the check did. And then same idea as before, if we can't just assume the check are consistent, we can downgrade, if you will, in the sense that instead of calculating per plot, we'll just drop down and calculate an overall treatment percent of check value. So we'll just take the mean of treatment 2, for example, and compare it to the mean of the check across all the replicates. If we can't assume, and we've got a lot of variation. So that was much like that T-tab before. We'll get one value for each treatment. Really nothing you can do statistically. You won't see any mean separation or any statistics because there's only one value for each treatment. So there's no variation. So thus we can't do ANOVA or anything like that, but you do get those numbers to have that there. And just like we saw with the T-tab with our percent check, you can calculate, this percent of check just on the report. Just slightly different code. It's the automatic percent of check, so APOC in that original column, and you'll see it on the report, just like we saw the APC value. So I won't say that all again. Show that all again. It's really the exact same concept, just different calculation basis. And I guess I didn't reference the picture in the corner, but make sure that you tell ARM what treatment is the untreated. So just because your treatment list might say UTC or check, ARM needs to kind of be told specifically what that is, and that's in your, that's in your trial settings on the treatment tab. And you would just list the treatment numbers. So this means treatment number 1 is my untreated check. If treatment 7 was the check, I would put the number 7 into that box. If you did have more than one check treatment, so if we wanted more than just one check within each replicate, you would have multiple check treatments in your treatment list. You would just put a space, 1 space 7, and that'll have both of them be marked as the check. And in any of these calculations, then when it's trying to calculate to the check, it'll take the average of whichever check values are in that replicate. If you're doing the Abbott's or the percent of check. Okay, moving on to our next topic then. A little bit shorter, fewer variations on the same calculation. Yield conversion. So this one might be probably the most common one because a very good portion of research ends up with running some yield numbers. And so ARM can take any raw yield values that have been recorded and calculate the yield on a per area basis. And so there is a wizard you can see on the right that can step you through the various components and conversions needed in order to do this. So there is, obviously just the baseline. I've recorded my weight in kilograms, but I want it to be in tons per hectare. That would fill in this conversion factor based on your plot width and length. ARM knows the area of your plot, so then can calculate based on that area and convert from kilograms to tons. So then a yield conversion factor gets filled in. Then there's additional tools to take it a little farther. There you can adjust the moisture. So you can adjust the values to a dry moisture percent that you specify. If you have average, your average moisture recorded for each plot, you can put that in a separate assessment column right next to your raw weight, in my example, kilograms. and have ARM utilize those moisture values in converting to the dry moisture percent that you specify. So then that kind of tosses out the conversion factor, because of course each number now will be a little bit different depending on the moisture in the associated column next to it. And then finally, there's the harvested plot size. So like I said, it fills in your width and length from your settings to calculate this conversion. But if you did have different harvested areas per plot, so if you weren't uniform, you had some of the plots where you had less of an area or more of an area harvested, you can account for that as well. Again, just create another assessment column that has the individual values, whether it's the width or the length, and that then ARM can use instead of the overall number. So it'll use all of those components to convert from the raw into our yield based on those parameters. And you would tell ARM where is the source, the raw weight, that's in kilograms, and then what assessment column should we fill in with this calculation. And number of decimals accuracy can be kind of important too, so you don't end up with tons and tons of digits that drive you nuts. So back to ARM, just to show that in place. I've got my, oh, really this should probably be our test weight. The raw test weight here that we harvested in kilograms, summarized for each plot, is our first column here, column number 6. Then, as I mentioned, if you have a moisture content, a moisture rating for each plot, then you have the ability to bring that in as its own column, and we can then utilize each value on its own as ARM goes through the calculation. And so then we can generate this converted yield. So I've already done that, but to simulate it again, I would just start in my test weight column, and under the tools menu, we can convert yield. And that will bring up this conversion dialog. And so what we have, tons per hectare. And you can see as you adjust this information, then that yield conversion factor changes. So maybe we don't harvest the entire plot. So this starts with the entire plot area, but maybe we only do the inside 2 rows. So maybe it's half of the length. That's probably the other way around, but that was easier for me to round. You can adjust that size there, and you'll notice then that conversion factor is changing as I change the parameters here, because this would then be the number that gets multiplied by our source column to end up with our yield. Then we do also have that moisture adjustment as well. And I can use a whole trial average if that's all I have is a whole trial average, but I may be able to be more specific with the data column. And that's what I did here. To specify that, I'll set this back to 9 so we get the same conversion as we did here. And converting column 6, in my case, I would put it in 8 since I already have that slot. It's going to warn me that I'm going to overwrite, but yes, that's the exact same calculation that we had. So now in column 8, the action code is TY3. So that shows that it's a yield conversion calculation stored in memory. And there we have our calculation. And just for fun, I also threw a percent of control onto that yield. Kind of circle back to that last discussion there. You can see that the check, our treatment number 1, is forced to 100. And then each value from there is calculated relative to it. So we ended up with 9.4 compared to 8.5. So about 110% of the check. You can see one of these plots clearly struggled and has been marked as damaged because something was not right. Only had about half the yield. So those have been marked as damaged over here. So if we were to run a report, that value is just tossed out and it's treated like a missing value. Okay, so that is our yield conversion. Moving to our next topic here is rating scales. I guess in some senses, this isn't just calculations. We're definitely talking about the calculations, but kind of also ties back to the assessment itself that's being performed. And there's a variety of calculations and different iterations or different options on the same type of calculation that we'll talk about. So I tried to split this out. There's, like I said, there's tons of rows in that action codes list that are related to rating scales, and it's a bit of a mess in there. So hopefully we'll have an overview here to kind of try to make sense of the different combinations and options of what you might want to do. So I wanted to start with the EPPO rating scales. And so EPPO defines some standard rating scales on certain pest and crop combinations. So I have a couple of them on the screen. I just picked them as 2 different types. Some of them are just kind of almost a category, 0, then a 1 to 2, 3 to 5, more than 5 on lesions on the beet, for example. Some of them are more of a range of a percent that's affected. So here looking at a particular blue mold of tobacco, and instead of having to differentiate, well, is this a 10% or 15% affected? It makes it easier on the researcher in that you're really just marking down that entire range. So this, well, 1 is always no incidence. So if there's no pests at all, that's easy. That's a 1. And then it just kind of slowly grows from there. So instead of having to be precise and differentiate what's a 15% and what's a 20, that's maybe hard to be consistent and not very easy to do. Instead, it's a matter of, well, is there a little bit less than 5%, or is it more than 5, so it would fall into this 3rd bucket? So makes it maybe a little easier for the human to do as going through the rating. So that's kind of the idea behind some of these scales. And so EPPO has went through and tried to define some scales to do that, and not just blindly picking numbers, but trying to be agronomically intelligent with the choice. And also, you'll notice that a lot of them are logarithmic, like this example. So, the second one here has just kind of a 5% band, if you will, relative to if we were just doing a general percent of incidence. You would have 5. Well, this next one has a width of 20, and then the next one's 25. So it's growing from just the regular scale. So you end up with this kind of logarithmic action there. For some of them, this one's fairly even on the left. So depending on the research, depending on the crop, they vary a little bit, but we've got a group that went out and tried to make it easy and define these standards for everyone to utilize. So they're all going to start at 1, just depending on how many groups they have. It might be a 1 to 4, it might be a 1 to 5, but always number 1 means no incidence, absolutely 0 for the response. So at least for the calculations in ARM, I don't know that this is for sure the way EPPO insists on documenting this, but in order to calculate what we're going to see on the next slide for these EPPO scales, really the only calculations for the EPPO scales we have use this system for documenting the assessment. And that is to make multiple assessment columns, and each column in ARM is the individual class. So basically, you're recording the number of samples that were in that class or scale. So for example, plot 102, maybe we looked at 10 different leaves. We're looking at leaf damage. Maybe we had 10 different leaves that we were looking at in each plot. Well, 2 of them had no incidence. They landed in category 1. Whereas 5 of the leaves had a rating of 3. So maybe we pluck 10 leaves off of our crop and then just put them in different piles. As to this is 0, 1, 2, 3. I guess I should say 1, 2, 3, 4, because the 0 is a 1. Anyway, put them into those 4 different groups and then just count how many they are. And that's the number that gets put into ARM. So we end up for a 1 to 4, we have 4 columns for this one rating that we did. When we set it up that way, then in the action codes, we have a couple of calculations we can do based on that assessment we performed. So the first calculation is incidence. So that would be the percent of samples that had any sort of presence of the pest. So the action code for that, at least for the 1 to 4, is at DIP 14. If there was a 1 to 5 scale, it's usually the exact same thing, DIP 15. So we'll have the different combinations depending on the specific scale you're using. But this calculation basically sums up columns out of that 4 that we were looking at in the last screen. Let me go back. Out of the 4 here, we're going to sum columns 2, 3, and 4. So let's take all of the ones that had anything other than 0. In this case, 2, 5, 1, that has 8, and divide that by the total number of samples we had, which was 8 plus 2, 10. So we'd end up with 80% for that plot. 80% of our leaves had some level of that pest. Now, if you want to factor in, well, how bad was the infestation? How bad was it? Then you would want to calculate an index or a severity. So there I have the pest severity calculation here. And that accounts for the intensity. So we're going to take column, in a way, we can take column 1. Yeah, S1 here, sorry. So take column 1, however many those are, and multiply it by 1, because that has kind of the baseline, nothing happened. Then however many we have for column 2, multiply that by 2. So we're kind of getting a weighted average. Say, hey, well, 2 is worse than 1, so those should count double. And then number 3 times 3. So if there may be fewer in group 3, but that is more significant, that there is more infestation. So those might weight themselves even higher than the 2s, even if numerically there was less. And so on until you get to the end. In this case, there's the 4. And then you would just divide by, again, that total number of assessments that we did. So we get this average then, this kind of weighted average of how bad was it? 2.5. So if you had all fours, so every single plot had the maximum amount of infestation, you would end up with a 4 for your severity. So this is basically the average value of the rating scale across all the different samples in that one plot. So a 2.5 is what we calculated for that first plot that we were talking about a second ago. Just to see that in ARM. And we looked at that screenshot, so I'll just click a little bit that we've got that category 1. And I use leaf damage because we had a part rated here that was handy for me, category 1 through 4. So we just were counting how many leaves landed in this category 1. And since it's an EPPO rating scale, we know that that means zero incidence. So there we had the 2. There were 2 out of the 10 total samples that we took. So I have number of subsamples as 1 because that tells ARM how many values to type in this column. So it would be 1 because I only have 1 value. If we wanted to, we could find the sample size, and we could put in 10 leaves as our sample size, since that is what we were actually sampling. But I want to make sure to point out number of subsamples is 1 in this case, because that's how many values ARM should present for us to fill in this column. So we fill in all of those, and then if we move over to the right, you can see those 2 calculations that I did. And just to show the list, to show the small mess that we add, if you will, there's a whole section calculating the index or the severity for our EPPO 1 to N rating scales. So if you're using a 1 to 2, 1 to 3, 1 to 4, it goes all the way up to 1 to 12. Just depending on which one you're doing, it's going to calculate that severity or calculate that index. And the N is the scale 1 column. So it does assume that you put all 4 of these together. So if you do category 1, you need to do the rest of them right next to it. So all 4 of them are together, which is somewhat logical anyway, because otherwise you'd kind of have a mess anyway. So that's the index or severity, and then the percent incidence. We have those as well for the different combinations. Certainly, there are other rating scales that can be done. And we have calculations that would do very similar things for us. So certainly all of the 0 to N, whatever ones those may be, we can still calculate an incidence and the index or severity. So if you want to calculate the incidence for a 0 to 4, so maybe there's 5 different groups, but it starts at 0, then we would do DI 0 to 4. The other thing we can do here, and my example shows using subsamples. So instead of having the count of how many were in category 1, how many were in category 2, you can simply have one assessment column. In my case, I've got 10 subsamples, and the value itself is the scale or the class that that sample fits into. So doing I guess in my case, it's damage to plants. So I'm looking at the first plant I need to rate, and it's a 0. No damage at all, perfect. Come to the next plant, oh, that's about 20% damage, or whatever my grouping is there. I'm working from a 0 to 3, so maybe it's more like 50%, but anyway, that would fit into a category 2. So I put down 2. And then category 1, etc. So you're putting the actual rating value, the scale value in as subsamples. A little bit more concise, just from how many columns am I creating in ARM, but numerically we can do the same things. Excuse me. We can calculate that incidence. So DI04 will calculate that exact same 80%. Either way, no matter what we do, if it's the same result, we get that same calculation of 80% that were not 0. In this case, the assumption being 0 is the no presence as opposed to 1 before. For the severity, there's actually 2 different options. So the DS04, that one does the same thing that we did with the EPPO a minute ago. So we were weighting the values, number 1, number 2, number 3 times 3 to weight how severe it is, and then we were just dividing by how many total. That can work obviously if we kind of have the same setup, the same type of scale where we've maybe grouped things. We've got perhaps that logarithmic setup for our scale levels. But there may be other scales that don't follow that same pattern. And there are other ways to calculate the severity. Just naturally speaking, how do we want to weight these items, these scales, and assign severity of how bad things really are? That might vary a little. The kind of the more common one, and I have a typo, I missed the B in Townsend-Huberger, is really to calculate this severity as a percentage. So the DS04, that is just kind of relative to the scale itself. So from 0 to 4, the average was 1.5 is basically what that will give us. The Townsend-Huberger is a percentage. So 37.5, that's really a percent of the severity. So again, if all of our samples were a 3, the maximum number, 33333, that would be 100% severe. Every sample was maxed out. And then of course, on the flip side, if every sample was 0, then the severity would be 0. And you just get the percent as you kind of add up all the severity amount, if you will, the amount of, in this case, damage to plants as you go. It's about 37.5% severe. So that's the Townsend-Huberger. So that would be at TH04S. And I'll show that in ARM in a moment, depending on how you want to fill it in. But we're doing something similar where we're weighting. So 1 times the first group, 2 times the second, 3 times the third, etc. But then we're dividing by the sum of all of them times 4, and then making a percent. So that's also available in ARM. And we did recently add more of those combinations. Let me toggle to the scale real quick just to show again those subsamples. So we just have one source column. We can calculate that percent incidence. The severity, like we do for EPPO, is at DS04. In this case, if you notice, the disease severity from subsamples it ends up actually being literally just the plot average of these subsamples. So whether or not you need that calculation, maybe you don't necessarily, because if you just run an AOV, the first thing ARM does with subsample data is average it. So you'll actually end up using that 1.5 anyway in the report. So there's not quite as many of those combinations, and I think that's why it's requested less, because numerically you get it kind of right out of the gate by just calculating the average of those values. But anyway, then that last item here, the Townsend-Huberger. Let me open that one up so we can see the correct name. I've got the Townsend-Huberger for 0 to 4. Actually is wrong for my calculation because I had 0 to 3. So let me adjust that as well. I should have chosen 0 to 3 being the assessment I did, and then there's an S to say it's from subsamples. So there is also the variation of calculating Townsend-Huberger, doing that percent severity on a 0 to 3 with the rating summarized at plot level in separate columns, which was the example we showed with the EPPO ratings. But there's nothing, EPPO isn't the only way, the only type of rating scale that you can use to summarize that way. So kind of two different systems for recording assessments like these. And then just depending on which one you chose, you can generate a Townsend-Huberger from either system. If you just want to go down and fill in subsamples, because in my case I had 10, that's pretty easy to manage. But if you're going to do 100 subsamples, that's a lot harder. Or just depending on what you're doing, it might be a lot easier to set the fruit into the different categories all lined up, on the ground, and then somebody can walk by and just say 2 of them are in group 1, 3 of them are in group 2, etc. So it kind of depends on where you're going there. So I should actually have this be Townsend-Huberger 0 to 3. And you'll see those numbers change based on that source column. So we're actually about 50%. There is actually a comment here, I guess, question and a comment. The first question was these action codes and how they would relate to SEs. So the action code creates the calculation in that column. This can be a great thing to capture in an SE. So an SE, if you haven't used those, standard evaluation, that encapsulates one or more columns, the descriptions of them into a file, so you can use that same description every time you perform that assessment. So this is a great example. If you do this often and you want these calculations to always be done with that assessment that you perform, a really good example to do that. And then just make sure to include the ARM action codes row when you're generating that SE. So that way the calculations will happen automatically when you load that SE. And then the other comment was just a side note about adding the actual scale number for each plot, but not add the average of a scale. So you wouldn't want to add 12.5% if the plot shows a severity between 5 and 20. Picking right between it, because the percent are identified as scale number 2. So you would put in the 2. So hopefully that's helpful. So some of this ends up falling into that realm that you can tell I don't know, because I'm not a researcher. So once we get into the real realm of how to pick these scales, then I'm a little less great at, because I don't actually perform the research. But hopefully I can crunch the numbers and it can make sense in my brain numerically. But yeah, how you actually want to select that scale and how to approach it yeah, kind of a whole nother world. You kind of got to be careful of how you're doing that. So thanks for that comment. All right, and we did get long-winded, so I'm going to try to get through this last section pretty quickly. Just a note on subsamples, we kind of saw a little bit there with the rating scales, but just any type of rating where you have subsamples, there are some calculations you can do based on that source column that has subsamples. So you could calculate an average of the subsamples just with TAS, or sum them. So if it's a yield type of situation and they're really accumulating across the different samples you're taking, you can sum them, and that'll just create a new column with that information. You can also calculate incidence, which can be related to the rating scale, but could be done for others as well. And that's really the percentage of subsample values that are larger than either 0 or 1. So depending on your assessment, sometimes 1 means nothing's there, like we saw with the EPPO rating scales, and probably all of the other cases, 0 means 0, that there's none. And so use TIO for that case. You can also count values within a range. TIN, that's, I think, a little more useful for this final topic that I wish I had a little more time to show, but I think the biggest thing is just to know that it's available. And it's user formulas, essentially much like you can do in Excel, where maybe you have data you've typed in, and then you go to another cell and you press the equals button, and there's this whole expansive library of calculations and equations, and you can fill in your own, and you just can reference a cell to add it to another cell and get a number. You can do something pretty similar in ARM as well. And so you just need to use, under the Tools menu, there's the Transform dialog and an option under there for User Formula. And that's basically like pressing the equal sign in Excel. You now have this box where you can type in a variety of commands to generate a calculated value based on whatever you want to calculate. So you can combine columns together. You just would refer to a column with brackets. So this would take, for plot 101, let's take the value from column 1 and add it to column 2. And if I store that in column 3, then that number that we calculated will be put in the calculated column for column 3. And there's a bunch of functions. If I just real quick go to, here's my formula, it'll create the T1 formula, but just Tools Transform. And there's this user formula. The best thing to do, press the Help button. And of course, it shows off my screen because I'm presenting. There we go. There's a bunch of transformations, a lot of them we talked about today, but the big one here in Help is to go to user formula. And this goes through a lot of different functions. Obviously, there's just equations you can do, but there are some functions that you can call. Those are kind of weird, but you can refer to different column numbers. You can utilize the check treatment in a calculation. You can use a header field as well if you use the code. So obviously, lot you can do. I definitely don't have time now to cover all of it, but you can use that help function here to kind of see some of the different things you can do. And that's really what I had in this last slide, is some of those tidbits that are all described in the help, or just send us an email. Again, I'm a math major, so I like doing numbers. So feel free to drop a question in the support. I want to calculate this. We can help you get the transformation that you might want to do. All right, so I ran long. Apologize if you had questions, but I do appreciate the few as we went through the session today. Feel free to reach out if you did have any calculations you're struggling with trying to make it work. Appreciate you all joining, and hopefully maybe we'll see you again soon at another webinar.
Thank you.
Yep, thank you.